Hello everyone, I am Himanshu Vasnani from Department of Mechanical Engineering and I am here to discuss with you on the subject Material Science. The code is ME207, unit number 5, lecture number 34 in the series. And today's topic are laminar composites, reinforced concrete, glass fiber reinforced polymer composite, and carbon fiber reinforced polymer composites. So learning objective for today's lecture are to provide the students with a basic understanding of laminar composites, reinforced concrete, glass fiber reinforced polymer composites, and carbon fiber reinforced polymer composites. A learning outcome of today's lecture will be the students have learned the basics of laminar composites, reinforced polymer, glass fiber, reinforced concrete, glass fiber reinforced polymer composites, and carbon fiber reinforced polymer composites. And students understood laminar composites and reinforced concrete in detail. So let's start with laminar composites. So when multi-directional stresses are imposed within a single plane, aligned layers that are fastened together one on top of another at different orientation are frequently utilized. So these are called laminar composites. Okay, and repeat once again, you can see it in the figure also. When multi-directional stresses are imposed within a single plane, aligned layers that are fastened together, one on top of another at different orientations, these are frequently utilized. Okay, these are called as laminar composites. These are generally designed to provide high strength, low cost at a lighter weight. Purpose is to provide high strength, low cost at lighter weights. So familiar laminar composite is plywood. We know plywood that we use in normal everyday life also. A familiar laminar composite is plywood where the veneers are joined by adhesives, typically phenolic or amine resins. So the individual odd number of piles are stacked so that the grain in each layer runs perpendicular to that of the layers above and below it. We have seen this in the figure also. So this technique offers plywood that is strong and yet cheaper. You can see in the figure the stacking of successive oriented fiber reinforced layers in this laminar composite. Okay, now let's do the next slide. Now some safety glass is a laminated structure wherein adhesive such as polyvinyl material is used between two layers to keep the glass from flying when broken. Now this is really interesting. Okay, we know this when you broke the glass, it doesn't get you can say dispersed outside. It remains broken within the film only. Now formica is another common laminate used for countertops. Now laminates require two or more layers to be bonded together. So laminations may also be constructed using fabric materials such as cotton, paper, or woven glass fibers embedded in a plastic matrix. So obviously, a laminar composite has relatively high strength in a number of directions in the two-dimensional plane. However, the strength in any given direction is of course lower than it would be if all the fibers were oriented in that direction. Applications involving totally multi-directional applied stresses generally use discontinuous fibers, which are randomly oriented in the matrix material. Okay, what they use generally go for discontinuous fibers, and these are randomly oriented in the matrix material. So the reinforced efficiency is found only one-fifth that of an aligned composite in the longitudinal direction. What they say? The reinforced efficiency is found only one fifth that of the aligned composite in the longitudinal direction. However, the mechanical characteristics are isotropic. So for a particular composite, consideration of orientation and fiber length will depend on the level and nature of the applied stress as well as the fabrication cost. The short fiber composites, both aligned and randomly oriented, production rates are rapid, okay, and intricate shapes can be formed that are not possible with continuous fiber reinforcement. So moreover, the fabrication cost, cost matters a lot. So here the fabrication costs are considerably lower than for continuous and aligned. Okay, so you can see how this short fiber composites will be helpful. They have high production rates. They can produce intricate shapes also. Okay, and then the cost is also low. So very, you can say, positive features. Now sandwich structures. Now these have thin layers of facing materials over a low density material or comcore such as polymer foam or expanded metal structure. Okay. Now familiar sandwich structure composite is corrugated cardboard. The corrugated paper core is covered by two faces of thin paper. So in this structure of this type, the facing material serves to fix the inner core in place. What the facing material that we are using, it serves to fix the inner core in place. So the core provides the strength. I repeat, understand this thing. In structures of this type, the the facing material, it serves to fix the inner core in place. So the core provides the strength. Now, typical face materials include like aluminum alloys, fiber reinforced plastics, titanium, steel, plywood. You can see this in the figure also. You're given you a honeycomb structure. You can see there is a face sheet, then you have the adhesive below that. Before you have the honeycomb, and then again the adhesive is there, and again the face sheet is there. You can see the honeycomb is between the adhesive and the face sheet. The face sheet is on the upper layer. Now, if you see after in the right hand side a diagram, which is a fabricated sandwich panel. Okay, this is how it looks. The main thing is that in this type of structures, the facing material serves to fix the inner core in place. The core provides the strength. Yeah, you can see this in the figure also. Now, structurally, the core serves two purposes. First, it provides the faces and resists deformation. It separates the faces and resists deformation perpendicular to the plane face, to the face plane, perpendicular to the face plane. And secondly, it provides a certain degree of shear rigidity along planes that are perpendicular to the faces. Okay, the two purposes are it separates the faces and resists deformations perpendicular to the face plane. And second is it provides a certain degree of shear rigidity along planes that are perpendicular to the face. Foam polymers, synthetic rubbers, inorganic cements, balsa wood, etc. materials and structures are used for cores. The core has lower stiffness and lower strength. Another popular core consists of a honeycomb structure. You can see this in the figure. The honeycomb structure is there, which finds wide use in industries such as aircraft industry. Where high strength and lower weight are important factors. In the aircraft industry, we require higher strength and lower weight, which is the basic you can say factors for selecting the material. A honeycomb structure it consists of a thin foil that have been formed into interlocking hexagonal cells with axis oriented perpendicular to the face planes, or you can say face panels. What they say, this honeycomb structure it consists of thin foils that have been formed into interlocking hexagonal cells with axis perpendicular to the face panels. Now the material used may be similar to the face material. The material used may be similar to the face material. So these structures these are lightweight, they are stiff, they are strong, and then can be filled to provide sound and vibration damping. Okay? They can be filled to provide sound and vibration damping. You can see this structure in this figure also. The main thing from this thing that the honeycomb structure consists of a thin foils that have been formed into interlocking hexagonal cells with axis oriented perpendicular to the face panels, and the materials may be similar to the face material. Okay, and this structure, these are light in weight, these are stiff, these are strong. Okay, now continuous and aligned fiber composites, just some of that. The mechanical behavior of this type of composite, it depends on stress strain behavior of fiber and matrix material. The phase volume fractions. The second is the phase volume fraction. The third is the direction in which the stress or load is applied. I repeat all the three, you can say, behavior. The mechanical behavior of this type of composite depends on the factors, that is the stress strain behavior of fiber and matrix phases. Stress strain behavior of fiber and matrix phases, the first factor. Then the phase volume fractions, and then the direction in which the stress or load is applied. So moreover, the properties of a composite having its fibers aligned are highly anisotropic. That is, the dependent on the direction in which they are original. Okay, we have discussed all the three factors: the direction in which the stresses or load is applied. Then they say that the properties of a composite having its fibers aligned are highly anisotropic. That is, they depend on the direction in which they are measured. Now let's talk about a very important topic: reinforced concrete. Reinforced concrete. Now one can increase the strength of Portland cement concrete by additional reinforcement. Okay, one can achieve this by means of steel rods, wires, bars, or mesh, which are embedded into a fresh and uncured concrete. Obviously, the reinforcement renders the hardened structure capable of supporting greater tensile, compressive, and shear stresses. You can see in this diagram when you have a plain concrete, how it is happening. When you have reinforced concrete, that how its support is there. When you have pre-stressed concrete, now it's functioning. So it will give you a clearing idea what support it can be. So considerable reinforcement is maintained even when cracks develop in the concrete. So the coefficient of thermal expansion of for steel is nearly same as that of concrete, and thus it serves as a suitable reinforcement. Okay. So moreover, the steel is not rapidly corroded in the cement environment. We know that here the steel is not rapidly corroded in the cement environment. And also a relatively strong adhesive bond is formed between it and the curved concrete. What to say? A relatively strong adhesive bond is formed between it and the curved concrete. So here when you talk about reinforced concrete and they say that the steel here in this is not rapidly corroded in in the cement environment, and also a relatively strong adhesive bond is formed between it and the curved concrete. Now, one can enhance this relation by the incorporation of contours into the surface of the steel member. This permits a high degree of interlocking. What this is? Interlocking. Now there is another reinforcement technique of strengthening concrete. This involves the production of residual compressive strengths. What is it? This involves the production of residual compressive stresses into the structural member. So the resulting material is called pre-stressed concrete. Okay, you are now you what you are doing? You are trying to strengthen concrete. Okay, this is we can say this involves the introduction of residual compressive stresses into a structural member, and the resulting material is called as pre-stressed concrete when seen in this diagram. The characteristics of brittle ceramics is that is they are stronger in compression than in the tension is utilized in this method. So obviously to fracture a pre-stressed concrete member, the magnitude of pre-compressive stress must be exceeded by an applied tensile stress. Okay. The important thing is that The another reinforcement technique to strengthen concrete, you have that you can do this by involving the introduction of residual compressive stresses into a structural member, and this resulting material is called as pre-stressed concrete. Now, in one pre-stressed technique inside the empty molds, high-strength steel wires are positioned and stressed with a high tensile force, which is maintained constant. Okay, in one piece this technique, they say inside the empty mold, high strength steel wires are positioned and stressed with a high tensile force, which is maintained constant. So after placing the concrete and allowing them to harden, the tension is released. So as the wires contract, they put the surface in a state of compression because the stress is transmitted. The stress is transmitted to the concrete through the concrete wire bond that is formed. There is also another technique known as post-tensioning. What is called as post-tensioning. Another technique known as post-tensioning. So in this technique, stresses are applied after the concrete hardens. Well, there is another technique known as post-tensioning, and in this technique, stresses are applied after the concrete hardens. The sheet metal or rubber tubes. What they say? In this, you can call after this, you can say sheet metal or rubber tubes are situated inside and pass through the concrete forms around which the concrete is cast. Now, sheet wires are fed through resulting holes after the cement has hardened, and tension is applied to the wires through jacks attached and embedded to the faces of the structure. They say the steel wires are these are fed. Here we got more steel wires. The steel wires are fed through the resulting holes after the cement has hardened, and tension is applied to the wires through jacks attached and embedded to the faces of the structure. So a compressor stress is imposed. Compressor stress is imposed on the concrete piece this time by the jacks. So to provide the wire to protect the wire from corrosion, the empty spaces inside the tubing are filled finally with grout. We're trying to protect the wire from corrosion. So you want to do the empty spaces inside the tubing are filled finally with a grout. So the concrete that is pre-stressed would be of high quality, and there must be a low shrinkage and low creep rate. Usually pre-stressed concretes are prefabricated and more used mostly for railway bridges and highways. Now come the polymer matrix components. You can see this in the figure also. You have to. So these materials consist of a polymer resins. Okay, what do they consist of a polymer resins? Here, resins denote a high molecular weight reinforcing plastic as the matrix with fibers as a reinforcing medium. So, in light of their room temperature properties, ease of fabrication, and cost, these polymer matrix composites these are used in the greatest diversity of composite applications as well as in huge quantities. So, in accordance with the reinforcement type, that is the glass, carbon, and aramid, various classifications of polymer metric composites along with the applications and the various polymer resins that are used here are as follows. The first is the glass fiber reinforced polymer composite, commonly known as GFRP. Now, in this, fiberglass is a composite consisting of glass fibers which may be continuous or discontinuous and contained within a polymer matrix. Now, these are commonly produced in e-glass. E-glass is for electrical because it draws well and has good strength and stiffness. Like a typical composition of, you can say, the weight percent would be that 52 SiO2, then 17 CaO, 14 Al2O3, then 10 Pa2SO3, with some oxides of magnesium, sodium, and potassium. And molten glass is gravity fed into the series of platinum bushings, each of which has several hundred holes in its base. Okay, so fine glass filaments are drawn mechanically as the glass explodes from the holes, then wound onto the drum at exceeds of several thousand meters per minute. At speeds of several thousand meters per minute. Okay, let's go with this. Now, the strength of this glass fiber is dependent upon the surface damage. What to say? This strength is dependent upon the surface damage arising when they rub against each other during processing. The application of a size, you can say coating at early stage during manufacture minimizes this degradation. What they say? The application of a size coating earlier at the early stage during manufacturing, it minimizes this degradation in the properties. So by reducing the propensity for forming these drift cracks. So the size consists of an emulsified polymer in water and also has effect of binding the fibers. What do you say? The size of an emulsified polymer in water and also has the effect of binding the fibers together for ease of further processing. With fiberglass applications like for automotives and marine bodies, plastic bodies, industrial flooring, and containers. In order to decrease this vehicle weight and boost fuel efficiency, the transport industries are utilizing to maximum extent of glass fiber reinforced plastic. Okay, you can see the applications are like automotive and marine bodies, plastic pipes, industrial flooring, containers. Okay, these are very important applications if you try to look about from industry point of view. Now, second is the carbon fiber reinforced polymer composite. Okay, so let's discuss about it. Now, they say that these consist of small crystalline of graphite. The atoms in the basal planes are held together by very strong covalent bonds, and they are weak. There are weak van der Waals forces between the layers. What I say? The atoms in the basal planes are held together by very strong covalent bonds, and there are weak van der Waals forces between the layers. So to obtain high modulus and high strength, the layer planes of the graphite have to be aligned parallel to the axis of fiber. Okay, what to do? The planes of the graphite have to be aligned parallel to the axis of the fiber. And the composite modulus, what is the composite modulus of carbon fibers? It depends on the degree of perfection of alignment of atom planes. So here this is you can say about information about carbon fiber reinforced polymer compounds. Okay, you can see this in the diagram also how this CFRP board is shown to you having plain weaves. And if you talk about that, then you can see this carbon fiber is in this between the epoxy matrix. This is how it looks. And the diagram is also very clear. Now this, excuse me, right. Now this varies considerably with the particular manufacturing route adopted, of which there are three main possibilities. See, if you see with this diagram, you can understand is how this carbon fiber is between the epoxy matrix. Okay, so you should understand this thing. Now this varies considerably with the particular manufacturing route developed, of which there are three main possibilities. Now talking in detail. Okay, with the help of these diagrams. Now starting with the polymer pan, that is polycrylonitrile, which closely resembles the polythene polyethylene in molecular conformations. It is converted into a fiber and is stressed to produce alignment of a molecular chain along the fiber axis. So while still under tension, it is heated in oxygen to form crosslinks between the ladder molecules and finally chemically reduced you can to give at high temperatures a graphic structure. Now the final gasification temperature determines whether the fiber have maximum stiffness but a relatively low stress, that is type 1 fibers, or whether they develop maximum strength at type 2. Now alternatively, these fibers may be produced by melt spinning molten pitch. Now, during the spinning process, the orifice causes the planar molecules. What happened during the spinning process? This orifles, this causes the planar molecules to become aligned. Now it is then hardened, or you can say it is then treated while it's held under tension in order to maintain its preferred orientation at temperatures up to 2000 degrees centigrade to form the requisite waves of graphite. It is also possible to stretch either of the fiber types described above during the graphitification stage, giving further orientation to of the parallel layers of the layers parallel to the fiber axis. The carbon fibers have the highest specific modulus and specific strength of all reinforcing fiber materials. The carbon fibers retain their high tensile modulus and high strength at elevated temperatures. Okay, now, however, the high carbon, high temperature, however, the temperature oxidation may be a problem because the carbon fibers are not affected, we can say, by moisture or a wide variety of solvents like acids and bases at room temperature. These carbon fibers exhibit a diversity of physical and mechanical characteristics. Okay, they offer a, you can say, exhibit a diversity of physical and mechanical characteristics, allowing composites incorporating these fibers to have a specific engineering properties. Now, on the basis of tensile modulus, what is it? On the basis of this tensile modulus, carbon fibers can have four classes. First is standard, then intermediate, then high and ultra high modulus. So fiber diameters generally range between 4 to 10 mm only. Okay, so both you can say continuous and chopped form. What do you say? Continuous and chopped form of these polymers are available. However, the modern fibers are usually however, carbon fibers these are usually coated with a protective epoxy size that also improves adhesion with the polymer matrix. So to talk about these fibers, then I say that there's both continuous and chopped form of these fibers these are available. So carbon fibers are usually coated with a protective epoxy size that also improves adhesion with the polymer matrix. Now, carbon reinforced polymer composites these are extensively used in sports and recreational equipments like fishing rods and golf clubs. Filament wound. What do you call filament wound? These rocket into the motor cases and you can say pressure vessels and aircraft structural components, both military and commercial, fixed wings and helicopters. So this is how this is done. Now, third one is aramid fiber reinforced polymer composites. Now, aramid fiber, these are high strength. What? These are what? These are high strength, high modulus materials, specially desirable for their outstanding strength to weight ratio. What we say? Their outstanding strength to weight ratio, which are supporting, which are superior to metals, not supporting, superior to metals. Ceramic fibers are high strength, high modulus materials, especially desirable for the outstanding strength to weight ratio, which are superior to metals. So chemically, want to take about that. This group of materials is called as polyparathene terephthalamide. Okay, what we call this group of materials is called as polyparathene terephthalamide. So there are a number of aramid materials. To name of two of these common materials are like Calver and Novex. So Calver has several grades like Calver 29 or 49 or 149 that have different mechanical behaviors. Okay, these have different mechanical behaviors like the chemistry and anode of chain alignment for aramid Calver are shown in this figure 8. You can see this, there are more and chain structures for aramid calvus fibers. This is how this fiber direction is shown to you. Okay, and you can see that how much per unit is used in this. Now these fibers that have longitudinal tensile strength and tensile moduli, and they are higher than for other polymeric fiber materials, but they are relatively weak in comparison. Okay, so To talk about these things, then these fibers, these are longitudinally, these have longitudinally tensile strength and tensile moduli, and they are higher than other polymeric fiber materials, but they are relatively weak in compression. Now, this material is also to creep and fatigue failure. So, although aramids are thermoplastics, you can say they are nevertheless resistant to combustion. Okay, these aramids, these are thermoplastics. They are nevertheless resistant to combustion and stable to relatively high temperatures. You can say these materials, these are known for its toughness, impact resistance, resistance to creep, fatigue failure. These are some features. जो है ना? And these aramids, these are thermoplastics. They are nevertheless resistant to combustion and stable to relatively high temperatures. So the temperatures range over which aramids retain their high mechanical properties is between 200 to 200 degrees centigrade. This is the temperature range, okay, in which they have their high mechanical these properties like minus 200 to 200 degrees centigrade. Now, aramids these are susceptible to degradation. What? The aramids are susceptible to degradation by strong acids and bases, but they are relatively inert in other solvents and chemicals. So, usually, aramid fibers these are used in composites having polymer matrices. Okay, these aramids these are susceptible to degradation by strong acids and bases, but they are relatively inert in other solvents and chemicals. Usually, aramid fibers these are used in composites having polymer matrices. Okay, so common matrix materials are the epoxies and polyesters. Okay, aramid fibers are relatively flexible and somewhat flexible. Aramid poly composites are used in ballistic products like waterproof vests and sporting goods and tires and ropes and missile cases, pressure levels, and as a replacement of asbestos in automotive brakes and clutch linings and gaskets. So a wide range of applications for this aramid composites. Okay, because they are known for its toughness, impact resistance, and resistance to creep and fatigue failure. So this has a wide range of applications. Okay, now reinforced polymers. One of the very important topic, reinforced polymers. Now, these are properties have been altered through the use of reinforced material. Through the use of reinforced material. Now, glass, minerals, carbon fibers, these can be added to polymers to alter their properties. We talk about reinforced polymers, what they say. These are polymers whose properties have been altered through the use of reinforcement material. Now, glass, mineral, and carbon fibers that can be added to polymers to alter their properties. Now, most polymers are available as glass fiber reinforced products. So, the glass fibers, okay, these most polymers are available as glass fiber reinforced products, and these the glass fibers whose diameters range from 0.0002 to 0.001 inch in diameter are coated with a resin and a coupling. The property increases of by about 2% or better may be obtained with the glass fiber reinforcement. The strength of these reinforced polymers it depends on the type and quantity of filler used and the degree to which the resins have wetted the reinforcement material. Okay, now strength. You can talk about strength of this reinforced polymer. Normally depend on the type and the quantity of filler used and the degree to which the resin has wetted the reinforcement. Now, what are more common filler materials in this glass fiber? You can see that this common filler material is glass fiber. Now, carbon fiber reinforced materials are more expensive than fiber reinforced materials. So, carbon fiber reinforced materials have high tensile strength and stiffness and greater relative mechanical properties. What we say? Then carbon fiber reinforced materials is a high tensile strength, the stiffness is more, and then greater related mechanical properties. So they also produce lower coefficients of expansion, improved creep resistance, and better wear resistance, obviously better wear resistance, greater toughness, and higher strength to weight ratio. High strength to weight ratio, and then glass fiber reinforced materials. Okay, so glass and carbon are the most common fiber reinforcements. This is how you can understand that there is a difference between carbon fiber reinforced materials and the other. So obviously, this fiber reinforced material. So obviously, you can see that the features of this carbon fiber reinforced materials are better, and that is why they are more used than glass fiber reinforced material. Okay, this is how. That's all. Other materials used in fiber reinforcements include graphite, boron, and cotton. And reinforcement materials are available in several forms, including mat, bundles, choppers, fibers, and cloth. Now these all things are viable because we have discussed these in the last para, the various features that were there in this material. So due to this, now you can see that the applications are in front of you, that these reinforced materials are available in several forms, including mat, fiber bundles, chopper fibers, and cloth. Now, most of the reinforced thermostatic polymers, like 90 to 25%, these are polyesters and epoxies, with the majority being polyesters. Okay, so these reinforced polymers, these are manufactured through a variety of products, like including hand layup, spray up, matched molding, premixed molding, and vacuum or pressure backcasting. Now, these materials are replacing metals in a variety of applications. They offer similar or better strength characteristics at lower weight and often at lower cost. Okay, these offer at lower weight you have good characteristics and also at lower cost. Now they are frequently easier to, you can say, produce, are resistant to corrosion and chemicals. What do you say? These are frequently easier to produce. Okay, so this is really good and very positive point, that they are frequently easier to produce, are resistant to corrosion and chemicals, and offer a wide variety of manufacturing processes, from the very simple and inexpensive to the same, you can say, to the higher volume and more intricate parts. Okay, the thing is, they offer a wide variety of manufacturing processes, from the very simple and expensive and very simple and expensive to the higher volume and more intricate processes. Now, laminar composites, very important. Now, when multi-dimensional stresses are imposed with a single plane, okay, these aligned layers that are fastened together one on top of another are different orientations of frequent reply. These are called as laminar composites. So I have also discussed here, the starting also. So here also you can see that this is used because they are strong and these are cheaper. This is the basic thing of this. Now, fabrication of fibers and films. Okay, so this is very important thing that I think we should discuss in a very, you can say, short manner. Like, so the fabrication of fibers and films. When we talk about fibers, so the process by which fibers are formed from bulk polymer materials called as spinning. Okay, not just, you can say, have a small idea of these things also. Now, most often these fibers are spun from the molten state in the process called as melt spinning. Okay, you can see this in the diagram. The three kinds of spinning: melt spinning, dry spinning, and wet spinning. So the first you have this kind of a melt spinning, and how this stretching is done and how this winding is done. You have in the melt spinning compound, you have the spinning pump, and then you have the spinning nozzle in front of you with have your cold air, and the air outlet is there. Then you have a winding unit available. Okay, you see. Now, the most often these fibers are spun from the molten state in the process called as melt spinning. So first the material is to be spun is heated, until it forms a relatively viscous liquid, and then it is pumped down. What are you doing? Then it is pumped down through a plate called a spinnerette, which contains numerous small round holes. So when the molten metal passes through each of the orifices, a single fiber is formed. Each solidifies almost immediately upon passing through the air. What do you say? When molten metal passes through each of these orifices, a single fiber is formed and which solidifies utmost immediately, almost immediately upon passing through the air. So this is really interesting. The crystallinity of a spun fiber will depend on its rate of cooling during the process of spinning, and the strength of fibers is improved by a post-forming process called as drawing. However, drawing is simply the mechanical elongation of a fiber in the direction of its axis. Okay, so here this you can say the molecular chains during this process become oriented in the direction of drawing, such as the tensile strength, motor elasticity, and toughness are improved to a certain extent. Although the mechanical strength of a drawn fiber is improved in the axial direction, the strength is reduced in the transverse or radial direction. So moreover, since fibers are normally stressed only along the axis, this strength differential is not critical. So the cross section of a drawn fiber is nearly circular and the properties are uniform throughout this cross section. And about films. Now, many films are simply extruded through a, you can see this, many films are simply extruded through a thin die slit, and then this may be followed by a rolling operation that serves to reduce thickness and improve strength. Talking about films, these films, these are very commonly used materials. Now, this many films are simply extruded. Okay, what we do? Many films are simply extruded through a thin die slit, and then this may be passed. This may be followed by a rolling operation that serves to reduce the thickness and improve strength. Okay, so alternatively, a film may be blown continuously being extruded through another die, or then may by maintaining a very carefully controlled positive gas pressure inside the tube. So one may reduce wall thickness continuously to produce a thin cylindrical film which may be cut and laid flat. Some of the newer films that are produced by co-extrusion, that is multi-layers of more than one polymer type, are extruded simultaneously. So for these films, just remember one thing that many films are simply extruded through a thin dry slit, and then this may be followed by a rolling operation that serves to reduce thickness and improve strength. This is important. Now, this about this coupler is there at a relatively new group of metals that exhibit an interesting and practical phenomenon via the shape memory alloys. So one of these metals, these after having been deformed, has the ability to return to its predetermined size and shape upon being subjected to an appropriate heat treatment. I repeat, one of these materials after having been deformed. Okay, one of the materials after having been deformed, it has the ability to return to the predetermined size and shape upon being subjected to appropriate heat treatment. Okay, they have the ability to return to the predetermined size and shape. This is really good. Okay, after having been deformed, they have the ability to return to they have the ability to return to predetermined size and shape, predeformed size and shape, upon being subjected to a appropriate heat treatment. So that is the material remembers its previous size and shape. So deformation normally is carried out at a relatively low temperature where a shape memory occurs upon heating. So materials that have been found to be capable of recovering significant amounts of deformation at strain are nickel titanium alloys. Okay, the short form is nitinol. And some copper based alloys like this copper zinc aluminum or copper aluminum nickel alloys. So one of the important thing that there are some materials that after having been deformed, they have the ability to return to its pre-deformed size and shape upon being subjected to an appropriate heat treatment. That is, the material remembers its previous size and shape. The material remembers its previous size and shape. So this is really interesting. Okay. One important SM application is the weldness, that is shrink to pipe couplers used for hydraulic lines on aircraft, for joints on undersea pipelines, and for plumbing on ships and submarines. Okay, these are some you can say applications like each coupler in the form of cylindrical sleeve fabricated so as to have an inside diameter slightly smaller than the outside diameter of the pipes to be joined. It is then stretched circumferentially at some temperature well into the ambient. So next the coupler is fitted over the pipe junction and then heat it to room temperature. Heating causes the coupler to shrink back to its original diameter, thus creating a tight seal between the two pipe sections. There is a host of other applications for allowing displaying this effect. For example, eyeglass frames, strengthening braces, collapsible antennas, greenhouse window openers, anti-scale control valves on showers, women's foundations, and fire sprinkler biomedical applications. So shape memory alloys also fall into classification of smart materials. Obviously, these are smart materials since they sense and respond to the environment and its temperature changes. So obviously, this is very important thing. That material remembers this previous size and shape. I'm really very good. Now some MCQs. Now the fiberglass is a mixture of glass fibers. What they say? These fiberglass is a mixture of glass fibers embedded in a resin matrix, which is a fiber component. So it's true or false. So I think it's true in this case. The answer is A. A second question. The composite materials are superior to all other known structural materials in specific strength and stiffness. Okay, in specific strength and stiffness, and the high temperature strength, fatigue strength, and the properties. So desired combination of properties may be tailored in advance and realized in the manufacture of particular material. I think it's true in this case. The answer is A. The base or the matrix of composites may consist of metals or alloys, polymers, carbon, and ceramic materials. So I think it's true. The answer is true in this case. A is the answer. Now, the composite materials containing two or more different fillers are termed as complex reinforced composites. So it's true. A is the answer. Now, fillers, the components in a matrix composites and thus they are called strengtheners. So fillers possess high values of strength, hardness, and lasting modulus, but these characteristics should be substantially higher than those of the matrix. So we think it's true or false. So I think the things about this filler, these are the information in the matrix. I think it's true. The answer is A. Okay, the component is a uniformly distributed in the matrix. A is the answer. True. Now fiber reinforced composites, like these are strong fiber embedded in a what when you talk about the fiber reinforced composites, we see that these are strong fiber embedded in a softer matrix to produce products with high strength. What they say? These are strong fiber embedded in a softer matrix to produce products with high strength to weight ratios. So the matrix materials transmits the load to fibers which absorbs the stress. Okay, so this is you can say this and read it once again so that you will have a better understanding. The fiber reinforced composites, then these are strong fiber embedded in a softer matrix to produce products with higher strength to weight ratio. The matrix material transmits the loads to fibers which absorbs the stresses. So I think it's true. Here is the answer. So when multi-directional stresses are imposed within a single plane, aligned layers that are fastened together one on top of the another at different orientations are frequently utilized. These are called laminar composites. So I think it's true. A is the answer. A is the answer. No, the laminar components, these are generally designed to provide high strength and low cost at lighter weight. When we talk about laminar composites, these are generally designed to provide higher strength and low cost at a lighter weight. A familiar laminar composite is plywood, where the veneers are joined by adhesives, typically phenolic or amine resin. True is the answer. A. Now, for a particular composite, consideration of orientation and fiber strength. What is it? For a particular composite, consideration of orientation and fiber strength will depend on the level and nature of the applied stress as well as the fabrication cost. Okay, now this is, we can say, understand the statement first. For a particular composite, consideration of orientation and fiber length will depend on the level and nature of the applied stress at as well as the fabrication cost. The short fiber composites, both line and randomly oriented, production rates are rapid, intricate shapes can be formed that are not possible with continuous fiber oriented forms. So moreover, fabrication costs are considerably lower than that for continuous and rigid. So I think it's true. Here is the answer. But for a particular composite, consideration of orientation and fiber length will depend on the level and nature of the applied stresses as well as the fabrication cost. Okay, so this is well explained. So I think it's true. Here is the answer. Now the reinforced concrete. One can increase the strength of Portland cement increased concrete by additional reinforcement. Okay, you can increase One can increase the strength of Portland cement concrete by additional reinforcement. So one can achieve this by means of steel rods, wires, bars, or mesh, which are embedded into the fresh or uncured concrete. So obviously, the reinforcement renders the hardened structure or capable of supporting greater tensile, compressive, and shear stresses. Now, this is you can say understand the statement, and then you will understand the main crux of this. The reinforced concrete. Well, I say that one can increase the strength of Portland cement concrete by additional reinforcement. One can achieve this by means of steel rods, wires, bars, or mesh. Okay, which are embedded into the fresh and uncured concrete. So obviously, the reinforcement renders the hardened structure capable of supporting. Okay, what you will do? The reinforcement renders the hardened structure capable of supporting the tensile, compressive, and shear stresses. So I think it's true. A is the answer. These are the references which you can refer and increase your knowledge on these topics. Thank you.